Hello, everyone. Thanks for listening to my talk. So I'm going to talk about the dusty and salty winds of intermediate mass AGB stars. But let's start with some definitions. What do we mean when we say intermediate mass AGB stars? And where do they sit in relation to this picture that we have of AGB evolution? Well, I mean, they sit in this picture relatively nicely. That's fine. What we mean when we say intermediate mass star is stars with masses above about 4 solar masses. So at solar metallicity is probably 4 to 8 solar masses. That's what I'm talking about when I say intermediate mass stars. So the key difference between the intermediates and the low mass stars is that the intermediate mass stars undergo hot bottom burning, which changes some of the nucleosynthesis products. So for example, oxygen 18 and carbon 12 are destroyed. So this means that despite subsequent dredge-ups, they can still end their lives oxygen-rich, not carbon-rich. That's because of the carbon-12 being destroyed. But okay, how can we tell the initial mass of an AGB star in general? For the low mass stars, we can use oxygen isotopic ratios. So this is where the relevance of the oxygen 18 comes in, because above 4 solar masses, it's destroyed and the ratio goes wild. Ooh. And the ratio goes wild, and we can't make any more predictions of initial mass. But as has been done in these 2 papers for several of our favorite AGB star sources, like some of the very well-studied ones, they all turn out to have low initial masses, mostly actually around 1 to 2 solar masses. But one way we can then say something is an intermediate mass star is if we have a good detection of a molecule with 17O in it, like a strong detection and no detection of the 18O. Of course, if everything's noisy, it all becomes a little ambiguous. So here is a list of known intermediate mass stars. I actually thought this list was slightly longer, but it's not. So there's 5. And I would say I'm relatively confident. The first 2, quite certain. Third one, reasonably confident. The other 2, probably. There's a few other candidates, but for reasons of signal to noise, we can't really confirm or deny. So this is something interesting to check later. A lot of the sources that you might think of that we study a lot are actually low mass, despite sharing some characteristics with this list. So in particular, I'll mention WX Pisces, which is an extremely dusty star. These are all extremely dusty stars, as you can deduce by the fact that their names start with OH. So they're all OHIR stars. But WX Pisces, despite being extremely dusty, has a low initial mass, around 1 or 2, I don't remember exactly. So, okay, we can say that these have intermediate masses, but 4 to 8 is actually, oh my goodness, 4 to 8 is actually a very large range. So can we narrow that down a bit? It has significant implications for the evolution lifetimes. So the answer is maybe. So based on Amanda's models, we can potentially use magnesium isotopes. So magnesium 24 is the main isotope, and then 25 and 26 are the slightly less abundant ones. But as you can hopefully see in this plot, depending on the initial mass, and this is at the end of the AGB phase, these lines, we end up with actually slightly more magnesium 25 than 24. And these dotted lines at the top are the solar abundance ratios. So they're quite different in the AGB stars. So, okay, magnesium, I mean, how are we going to see that? Those of you that know me know I study molecules. And the main magnesium-bearing molecules that have been detected are like MgCN and things like this in CW Leo, which Gulen found to have a solar isotopic ratio, which makes sense. We do know CW Leo, being a carbon star, is not an intermediate mass star. And those carbony magnesium molecules are not going to help us very much with the oxygen-rich stars. But this is where ALMA comes in. So we have well-resolved ALMA observations of these 2 sources, OH26 and OH30. And because of sort of choices of coverage and random chance, these lines are observed for both stars. I will talk about the last 3, which are much less common, in a few slides. For 26, just because it was a different ALMA configuration. We also have these common-ish, well, okay, the first three are common, PO a bit less, molecules, which it's not that they're not present in OH30, they just weren't really covered. They're probably there. It's not the point. But the other interesting molecule that was covered in OH26 but not in OH30 is one transition of MgS. Hopefully. I've asked for ALMA time to confirm this, so fingers crossed. But it's a pretty nice detection, like this is definitely a line. The original goal of these observations was to study CO and SiO. These are quite bright lines. The fact that we serendipitously detected MgS means that if we try like a little bit harder, you know, point ALMA at it for a little bit longer, that should be enough to check for the magnesium isotope lines as well. But first, we do need to confirm that this is MgS. Now, I can show you the integrated intensity map. It's a bit of a funny blob, not really centered on the star. Is this a problem? Not really. Turns out OH26 is just full of funny blobs, not really centered on the star. So originally, these two stars that I've just mentioned, OH26 and OH30, I was going to write a single paper saying, look, we see all these similar lines, but turns out dynamically, they're both a bit different and unique, so it's a bit too complicated for just one paper. And so I'll show you this preview, but OH26 has been deferred to the second paper. There is something weird going on here with these little streamer blobby things. I don't know. I mean, my initial thought is a binary, but actually maybe a triple. They're all very kind of consistently located, and this is pointing to like extremely hot water, shockingly far from the star, so there should be another heat source. And we see this in like all the lines that are optically thin enough to see the inner regions. So we can't see it in CO or like SiO v equals 0, but everything else. So that's weird. But now I'm going to talk about the other star. So OH30.1 doesn't have weird sort of molecular shapes, but it does have something weird going on in the continuum. We have a lot of dust centered on the star, but we also have this weird blob up here, which is a 10 sigma detection. And that's located 4.6 arc seconds, 4.6 arc seconds, you know, that way. North is up, east is left. So if we're saying that's coincident with a star, that's a projected separation of 18,000 AU, which is like a lot. Because we have band 3 and band 6 observations, this is the band 6 continuum, we can say that the the lower limit on the spectral index is actually already quite high. So what that suggests is that this is coal dust, maybe ice-covered dust, but like, why? why is it there? Is it actually associated with a star? So sort of from just looking at the continuum, there's kind of bridgey thing connecting it. It's not super clearly detected here, but suggests maybe it's associated, and I'll show you some more evidence in a few slides. But I promised I would talk about the weirder molecules. Oh no, sorry. Before I get to that, understanding this weird continuum blob requires understanding the context that we find OH30.1 in. And that means thinking a little bit about this massive star-forming region, W43. Why? Well, that's OH30.1 in the corner there. So in single dish observations especially, we see a lot of background contamination, and turns out that is because there is this background giant star forming region. This is a Spitzer image, and it is definitely behind the AGB star. They're not like physically interacting, it's just an annoying line of sight thing. But it does mess up our CO observations quite a lot. All the sort of pink stuff you can kind of see on the screen. You can see it a bit better on the computer screens, but there's a lot of random pink stuff that is just dust. So that's dust in the Spitzer range, but we still see it in ALMA. So here are the CO channel maps, and those diagonal band thingies that we see in several channels, that's ISM contamination, well, from W43. The way I've plotted this, the thick white lines, they're already 10 sigma. So it's quite bright, quite annoying, quite inconvenient. I've plotted like the 3 and 5 sigma lines a bit fainter to sort of focus on the CO coming from the AGB star, but it does mean that there are some channels that are just a bit rubbish, unfortunately. And it's even worse in the CO 1 to 0. And The other thing is that it's just bad luck. Like those two things are not close together, but the systemic velocity of the star happens to equal the systemic velocity of this cloud molecular star forming region thing. Okay, but enough about contamination. Let's focus on the CO. It's like shockingly round actually for an AGB star. Lane has already suggested that there's a binary in there, which I'll talk a bit more later. What I found from this analysis, you can see the contours are quite close together. The contours are just multiples of RMS. So the thickest one is 10, and then I think it goes 30, 50 sigma. They're all very close together, which is a very sharp edge to the emission. Also in velocity space, this one is 50 or something sigma, and that one's 30, I think. So this is a very sharp edge, which does suggest a high mass loss rate starting about 2,800 years ago, based on the size and the velocity. So from older work, from just dust modeling, K. Justinot found a mass loss rate of 1.8 by 10 to the minus 4, which is, I mean, in the ballpark of other extreme OHIR stars. Is this correct? Unclear. Detailed radio transfer modeling is deferred to a follow-up paper because it gets a bit complicated, but it is all very optically thick, I can tell you that much. Now, if we overplot the continuum, you can see that this sort of dimple that you might not have noticed before in the CO emission actually lines up with that second feature in the continuum. I'll now zoom in. So yeah, this little dimple, it lines up. So maybe that's slightly more evidence that whatever this continuum feature is, it is actually associated with the star, not some random like background, I don't know, hot Carino or something. Yeah. So I said I would talk about the weirder molecules that we see. So NS, we've observed it only with band 3 ALMA, which means the spatial resolution is lower, unfortunately. And while we can definitely see that this is off-center, the cross is the continuum peak of the AGB star, like we don't resolve any features. However, see that it is off-center. And this is reminiscent of the results I got for W. Aquilae, where we mainly looked at SAN. SAN wasn't covered here, but for W. Aquilae, we had a similar result for NS. And now here we have like a 5 sigma detection of NS. It's doing something. And it's actually exactly perpendicular to the location of this feature B thing. So that suggests maybe there is an eccentric orbit going this way. And somehow maybe that spat out a clump of dust for reasons unknown. But why I say a companion with an eccentric orbit is that NS formation is driven by UV photochemistry, as Marie has derived for us. So, I mean, that's the reasoning there. To really confirm this, we do need higher resolution observations of like a few more NS lines would be good. Another one was covered, but it's an intrinsically fainter line, so it didn't really help. The other two unusual molecules are NaCl and KCl, so salt molecules, and also note salt molecules, not not crystalline table salt. We see very highly excited lines of both of these. I've selected a few sort of random transitions, mainly just to show you that, yes, we do see up to V = 4. We see both isotopologues, so 35Cl and 37Cl, but also that even though the emission of the lower energy lines is resolved, it's not like we don't resolve any features. So we can't use this to derive anything about any binary orbits, for example. What we can think of is that NaCl formation has a very high activation energy. So it probably does need the extra energy from a nearby hot companion to form. So it probably is a companion tracer. But yeah, we can't say too much more about sort of specifics. It's probably a hot companion. I'm going to say B, maybe A star, but yeah, need more data. And I'll also show the KCl line just to prove that they exist. There are also more of these, but I ran out of space on the slide. And we see KCl up to V = 2. So as I said, the binarity of OH30.1 has been suggested before by Lane, where these features in the CO were deduced to be signs of the binary interaction, which is, probably the case, but they didn't study the continuum, and now we see this extra blob. The fact that it's coming off there means something. I mean, I'm not really sure what, but it means something. From these ALMA observations, we know that the separation between the AGB star and the companion should be less than 1,200 AU, which is not a very tight constraint. That's the resolution of the observations. So basically, we need higher resolution observations. So we already have some very nice images of the CO, so we'd just like detailed images of the inner wind. That should tell us a bit more. So just to talk a little bit more generally about the characteristics of intermediate mass stars from our sample size of 2.5. So of known intermediate mass stars, total sample size 5. So we have, studied half of them. So we know that they're very dusty, actually all 5 known very dusty. We see salt lines for 3 of them. So I've talked about OH 30.1 and 26.5. I also have an APEX spectral scan of AFGL 5379, which my student has been working on, hopefully coming soon. We see NS for both OH 30 and 26.5 in the ALMA observations. Unfortunately, APEX isn't sensitive enough to detect NS. We do detect NaCl in AFGL 5379, only in the ground state, but again, that's an APEX sensitivity issue. So I have talked quite a bit about salt. I will say salt is not unique to the intermediate mass stars. So for example, we've seen it in IK Tau, CW Leo, and a few of the O-rich stars from Atomium, all of which we know are not intermediate mass stars. And I just want to show this nice video that another student made. This is clouds of NS around IK Tau. The scale that we see here, as in the distance from the star, and this yellow dot here is the star to scale. This is much smaller than the scales at which we see NS for both OH26 and OH30. So even, well, I guess talking about the lowest energy lines there, but this is all much closer to the star. What we thought for IK Tau was that the salt was sort of formed in periodic bursts where an orbit of a companion, see it kind of looks like a spiral, was, every so often synchronized maybe with a pulsation or some other reason that there was extra shock heating at various times. Because as I said before, we do need the extra energy to form NaCl. So I'll leave up my summary there. So we have some intermediate mass stars. They need more study for us to understand them a bit more. They're very dusty, they're optically thick. The CO lines may suffer from ISM contamination, which does make life a bit more difficult. But with ALMA, we can study these less common molecules, which absolutely do not suffer from ISM contamination, so that does help. But we do need high resolution, high spatial resolution to really understand them fully. And I'll leave it there if anyone has any questions.
Hi, Taıssa. Nice talk. Can you derive carbon-12, carbon-13 for these stars to check if they're experiencing hot bottom burning or confirm?
Yes. So where those ratios have already been worked out, they are quite low.
Okay, that's good.
This is from,
I guess,
various literature sources.
Hi, nice talk. Could you use nitrogen isotopes to put some constraints on the initial mass, or it will be very hard to detect?
Nitrogen's a bit harder. The ratio between 14 and 15 is much larger. So, well, the ratio of like oxygen 17 and 18 is quite close, and same with the magnesium isotopes, but for nitrogen 14, 15, it was much larger. I don't remember the value off the top of my head, but it makes, detection a bit harder.
Yeah.
I mean, NS is quite a faint molecule, and HCN, what we do see like everywhere in oxygen-rich stars, the abundance isn't that high. So I think only like HCN nitrogen 15 has only been seen for carbon stars, I think.
Okay.
I can answer the question about nitrogen 14, 15. It's at least 10,000. The ratio between nitrogen 14, 15. Be very difficult to observe that.
Yeah, okay.
But I know Lucy Xeris's group has done it for a few carbon stars.
Yeah.
Taıssa, could it be potentially that the second blob in the continuum is the companion?
Probably not. Well, so firstly, the NS was pointing this way, so exactly perpendicular to this. So I think the periastron should be in this direction if it's eccentric. Well, it seems it is eccentric. I think it's a blob that was probably ejected during some sort of interaction, but why there's only sort of one blob, or maybe it was one big blob followed by these smaller ones that we don't see as well. That's unclear, and I will say that like a more detailed study on the nature of whatever is going on with this star in general is a future paper. But
Yeah, it's very interesting. And then on OH 26.5, the structures that you see, how do they align with the structures that you have in the carbon monoxide line? So where we have the spiralish things.
the CO spiral, oops, no,
Yes.
there we are.
Yeah.
I'm going to go through this slide again. The CO spiral is just, I mean, it's a much larger scale. At these scales in the CO, it's just optically thick and we don't really see anything.
Yeah, so you have you already made an image where you combine both so that you can see?
But
where
not
the
on my
things-
slides, but in general, I have checked. Yeah. There's also the SIO V equals 0 and I think SIS V equals 0 are also too optically thick to see this structure.
Yeah.
But anything that's sort of optically thin enough, we do see this in.
Yeah. And so if you have, then a potential idea might be to use a spiral binding or estimate it to have there some time estimate for the binarity.
Yeah, I mean, well, you did that in your paper.
Yeah, but I have then only the carbon monoxide so further out. So for instance, for CW Leo, we also see, or you also have seen that there is a different time span closer to the star and further away. So I will be interested to see whether that happens here as well. And that has been then the cause for the idea of potentially triple system there.
Yeah, unfortunately, the CO emission, even with sort of a bit of extra data reduction magic from Anita, is still fairly noisy compared with sort of these structures.
Yeah, but then I would really look to these structures and see if we can,
Yeah.
what you can get out.
Yeah, but like I said, the inner part of the CO is definitely optically thick.
Yeah, but you can use that for the inner part and then the CO for the out.
Mm.